All right, we're starting off this week with new stuff. Yes, we are transitioning from what is called electrostatics, which is basically you just have charges, they sit there, but they emit fields and voltages and all that kind of stuff and figure out those things. Now we're moving on to electrodynamics, which is now, okay, let's get these charges to move around and actually do things. Now, usually when you think going from something not moving to moving, that makes things more complicated. However, I would argue that this is actually uh, noticeably easier, especially to start. Okay, so when we get to things more complicated tomorrow, well, things get a bit more complicated. So we'll see how that actually ends up working. But for now, we're going to start fairly simple. So, and with that fairly simple question, we have a warm up question. Now, I'm not 100% sure if you exactly would know this off the top of your head, but just kind of think about it and answer the question, what is current? Okay, just what is it? What is current? Now, current has, of course, the electricity definition, but there's also sort of a general, for example, something like the water currents and stuff, right? And that definition still kind of works in terms of electricity. So think about how that comes together. Obviously, not like, the adjective current, but, yeah, so try to see what you can think about for a way of defining what current is, write something down, and then come back to this when you have that written. Okay, so current, the main way, if you're not sure about it in terms of electricity sense, again, I told you the hint about like water. And so what is water current? That's sort of like, it's a movement of water, right? You're taking water and it's moving at a steady rate, usually steady, from one place to another. It's a flow, okay? And so that's kind of the general sense here. So current in an electrical sense is that an electrical current is the flow of charge. Okay, you're taking charge and you're moving it through something at a fairly constant rate. Okay, so current is the flow of charge, aka the amount of charge passing through every second. Okay, it's the amount of charge passing through every second. So this is actually what's useful, right? In terms of actually building things and using electricity, right? Because if we just have a charge that's just sitting there, like it's just sitting there, right? What's it going to do? So we need to actually be moving through stuff to get things to happen. Now we have a mechanism for that because we've talked about voltage and potential energy. So for example, where is the question here? Okay, so this question that we had for homework a bit ago. It was involving calculating the charge in a battery, and then here's the potential energy inside of a battery. And so those electrons in the battery are given an energy which then causes them to move, right? And we have this speed at which the electrons are moving. Now, where do they go? Well, the battery's connected to things, right? Wires and whatever device is connected to, light bulbs, computers, whatever, right? So they move with a lot of speed, and that movement that allows them to go through things and cause things to happen. So this is current, and this is the mechanism for current. Voltage basically allows current to be there because it gives charges energy. So that's sort of what we're getting at. So now you may have heard about the unit of current. Okay, so charge. Probably not many of you have heard of coulombs before, but the unit for current is the ampere. Okay, the unit for current is the ampere, which is abbreviated as a capital A. It is defined as coulombs per second. Okay, so 1 ampere, also sometimes referred to as amps, but 1 ampere of current means 1 coulomb of charge passes through that thing every second. Now, I mentioned a while ago at the start of the unit how 1 coulomb is like a really big amount of charge, and how like the reason for that as to why the units are kind of weird I'll get to later. This is why. So current was actually figured out first. Okay, in the 1800s people figured out stuff about current. They didn't even know what electrons were. They didn't know what really atoms. Well, I don't know if they might have known what atoms were, but not like the theory of an atom in terms of like what it looks like, that wasn't a thing. So there was like, I don't know, there's this thing called current. There's this charge stuff and it's moving, and here's current and it does light bulb stuff, right? So they had this idea of a current, and so they had this. They came up with currents first, and then they sort of defined a coulomb from an ampere. Okay, so we introduced it as coulomb first, then ampere. It was actually discovered the other way around, or figured out the other way around. So the coulomb actually comes from the ampere, and so the ampere numbers are usually fairly reasonable. I mean, 1 amp of current is like kind of a lot, but it's not like ridiculously huge amount. Most like general electric devices that we have now like use less than that. But 1 amp is not like, oh my god, so much current. Well, 1 coulomb is a lot, and so the reason for that is kind of getting back to what we kind of talked about with this. So we have charges moving through things at really, really fast speeds. So this means that in 1 second, these electrons are going to move through this wiring like a million times, right? So sure, your charge that you have is not very much, right? That's the charge in the battery. But that charge moves through the stuff like millions of times a second. So it adds up, right? It's this times, several million or whatever, and you end up getting a number that's like, oh, how much charge passes through every second? Actually, not a ridiculously small number. So that's why the numbers here are kind of weird. But that's how this comes across. So, yeah. So the amp, that's kind of the whole thing with amps about like why they're kind of measured the way they are. So, but again, it's pretty standard in terms of how this goes. So, 1 amp of current equals 1 coulomb of charge passing through in 1 second. Okay, pretty straightforward in that sense there. Now, if you ever wonder about like what's the dangerous part of electricity, in terms of electric shock, like what is the thing that could actually be dangerous? The current is what is dangerous. Okay, so if you're talking about what can kill you or whatever, it is actually the current that is the thing that if it's high enough it can kill you. I'm not sure what the number is off the top of my head. I think I remember seeing like 7 amps can kill you or something like that. I'm not sure. I should have looked that up, but I forgot. I'm sure you can look it up yourself. But that's kind of how that's the deal with that. So now the current, which you can find the current stuff like a lot of plugs and stuff, especially like those here, let me grab my laptop charger. It's on the floor over here. Let me see. Like the boxes that are kind of seen on like laptop chargers, little box of stuff that you connect in. And there's a bunch of technical information on the back. If you ever look at that, you should see some things here. So for example, where do I see here? Yeah, okay. Okay, so here there's actually a couple different numbers listed. If you ever wonder what these boxes are, by the way, it's the fact that the current that's actually like is plugged into like the walls and the electrical outlets. It's a special type of current called alternating current. Basically, it's like it's not just straight up this amount of charge all the time. It's actually like a sine wave pattern that kind of makes things more complicated. It doesn't matter at this point. But basically, these boxes basically convert the current from what is inside the walls, inside the plugs, the outlets, into the type of current that your device actually uses. So and you'll notice there's like an input and an output. So basically it's saying that, hey, the input numbers is what's in the walls, and then that's converted into the output numbers as to what actually goes into your computer or phone or whatever, in terms of what the charger is. So it lists for the input and the output, it lists a voltage and an ampere number. And also for the input, it lists a hertz number, and that has to do with, again, the alternating current, that it has a rate at which the current actually, like, alternates. Alternating current's kind of complicated, so don't really worry too much about that. But you can see some numbers here. So, for example, the input says it's 1.3 amps, and the output says it's 2.31 amps. So it actually increases the strength of the current through this box. It does that, and actually the voltage goes down. So, yeah. So there's a couple interesting things about that you can see and how that works. So you can see a clear link between voltage and current. Because again, voltage is sort of the energy that you give to the charge, but then allows it to move, and you would have more of a current. So let me kind of write that in there. Voltage gives charges energy, which lets them move. therefore creating a current. Okay, so voltage sort of creates currents, it sustains currents. You can think of it kind of like an energy. I mean, that basically is what it is, right? Voltage is just energy, but it's per charge, right? So it's a way of sort of just talking about energy, but without dealing with charges, the individual charges anyway. So you have that sense there, but of course the current has to travel through something. And so currents travel through things, and different things are easier or harder for current to travel through. Right? You may have heard of the whole thing about like metal is a good conductor of electricity, right? What that really means is that just in a mathematical physics sense, that like it's easy for current to go through metal, right? It's a lot harder for current to go through wood or like rubber, right? It's a lot harder for current to do that. And there's atomic reasons that you kind of go over in chemistry as to why that works the way it is, but we don't really care about the specific details of that. We want to know kind of mathematically what's a way of describing that, right? What's a way of talking about this in terms of like, oh, this object is harder to go through than this other object. And so this is described mathematically as resistance. Okay, so electrical resistance. So electrical resistance describes how difficult it is for current to travel through it. And you can also describe this as how much voltage is needed to push the current through the object. Okay, so think of it again as like an energy situation, right? So if you're trying to like think of the current here moving through, is that we have the currents moving through something like a wire. A wire is a really thin piece of metal. You do not need really you need almost no energy to pass that, right? You need technically a little tiny bit, but it's so small it doesn't really matter. So the amount of energy that you sort of use up, the amount of voltage you use up to go through a wire is like almost nothing, right? But if you end up if the wire ends up connected to like even a metal thing like a light bulb, for example, you use up energy to go through the light bulb. It's not a ton, but it's more than, a wire. So a light bulb has a resistance, right? It's not a lot. Sometimes it could be kind of a decent amount, but it's not like millions or whatever. So, but if you had wire hooked up to like a piece of wood or rubber, the amount of voltage you would need to force that current through that object is huge. So because of that, the resistance of that object would be really big. So resistance is also measured. It has its own kind of mathematical thing. So resistance is measured, you may have heard of this, in ohms. Okay, so it's measured in ohms. Now the unit for ohms is actually an uppercase omega. Okay, so 1 ohm of resistance means you need 1 volt of voltage to pass 1 amp of current through the object. Okay, so it's all kind of related in this sense. So all three of these, the resistance, the current, and the voltage, are all related. So the more voltage you have, the more current you can pass through things of various resistance. If you have something with more resistance, that means you need more voltage in order to pass the current through, and vice versa. So they're all related. And all these three things come together. So these three terms come together in what is known as Ohm's law. Okay, the Ohm's law is very, very straightforward. That. Okay. Now, just to clarify what all these stand for. Well, V should be pretty obvious. V is your voltage in volts. Okay, pretty easy. R, you could probably guess, is your resistance in ohms. In your megas. Now, I is current. It's dumb that I is current. Remember, I was also intensity, and we used this before, so it's, again, kind of weird that you chose to use I, but that's what it is. So I is current in amperes, which is an A. Why? Because I don't know. So yeah. So how does this come into play? Okay, so let's say so here's kind of a question you could ask here. A light bulb with a resistance of 12 ohms is connected to a 5-volt battery. What will the current be through the light bulb? Okay. Well, we have V equals IR. We have and V is the voltage. We have that. It's the 5 volts in the battery. I is the current. Okay, remember, I is the current, but that's what we're asking for. We don't know what that is. And then R is the resistance. What is the resistance of the light bulb? Well, it's 12. Okay, so therefore, I is just 5 divided by 12, which is, I don't have this memorized. 0.43 repeating or something? 0.416, okay. 0.4167, say, amps. That's it. Like, this is pretty simple, right? The only really thing that's weird is that just I is current. That's the weird thing with that. So that's very, very straightforward. The thing that's challenging and what we're going to get into tomorrow is determining what this resistance is. Okay. Now there is a way to actually like figure out like, oh, if I have this object of this material that's like this length and this width, you can actually figure out what the resistance is that way. But that's not what I'm talking about. I'm talking about what if you have you probably, I mean, you might for in a really simple situation, but especially if you're talking about like stuff that's connected throughout like a house or whatever, you probably don't just have, one energy source, like one battery connected to one object, right? Think about all the things that are, all connected through wiring throughout a house, or even in a more simple example, you could talk about like Christmas lights. There's you don't just have one light connected to. Actually, Christmas lights are kind of their own special instance because if you ever notice with Christmas lights, they have kind of two wires coming in and out of them, and that's kind of its own special thing. But my point is, when you have multiple things connected, the actual resistance number and how you kind of figure out what a total resistance is, then it gets complicated. Okay? But it's ultimately all based off of this. Okay? So all this circuit stuff that we'll be doing with like the rest of the week, it all comes down to this formula. And you think that's a pretty simple formula, which it is. So I said this before, where the rules of this kind of stuff is easy, right? This is an easy formula. There's no real complicated things for any of this. The numbers aren't even terrible either, right? They're usually pretty, 12, 5, it's pretty straightforward. The challenge is, again, figuring out what this R is, which, again, is also still governed by straightforward rules. It's just it comes together in a very complicated manner. So this stuff's pretty easy to start with, right? There's really not too much to go at in this case. Now, there's a couple more things I want to get at. The first is that, and you may have seen this, that you can actually sort of draw. So this is, okay, let me start that sentence over. So far, this is an introduction to circuits, right? We have, what is a circuit? It's basically connecting, a battery or some sort of electrical energy source to objects to allow them to do things, okay? And so we have this example here is an extremely simple circuit, right? We have a battery just connected to a light bulb. Therefore, the electricity is going to come out of the battery through the light bulb. It's going to interact with the light bulb. The light bulb is going to do its thing. Basically, it's going to use up the electricity is going to use up its voltage in order to get through the light bulb and to power the light bulb, and then go back to the battery, get its energy back again, and then repeat, right? So we can sort of create diagrams of this. So this is actually a lab that you're going to be doing on Wednesday. And so you can create circuit diagrams. Now, there's a lot of stuff here which I'm not going to go over. It's sort of unnecessary. But there's a few things that are important. So let's start with this here. So this is a battery. Okay, and you can see here you can actually have the voltage of the battery. Now, this is the symbol for the battery, and you can notice I can change this so that, like, here's an actual normal battery. Couple things to notice for the shape. So remember, for this type of battery, this is the positive end of the battery, and this is the negative end of the battery. And how that's represented in terms of the diagram is by these two lines. You can't really see it that well because the thing's in the way. Let me turn off the values. So you can see you have a short line and then a longer line. The longer line is always the positive end of the battery. Okay, so that's the representative of that there. So then if we wanted to sort of, hook up a light bulb here, we can just turn this around. Connect that to that. And then there's a thing for light bulb here, but I'm actually not going to use that. Instead, I'm just going to use this thing here. It says resistor. So a resistor, is basically, don't worry about that. It's any sort of, here, can I that doesn't have to look pretty. A resistor is anything that has a resistance, okay? So there are some things that are actually just called resistors that you plug into things. Is there, let's see, does this switch all of it? Oh yeah, it does, okay. So this thing is a resistor. You may have seen these before if you've ever dealt with circuit stuff. I'm sure people who have done robotic stuff have probably seen these before. These are used basically as a way of generally actually just kind of lowering the energy for whatever you need. Sometimes you just don't need, a lot of energy for something. So you've probably seen these before, but generally you can kind of describe anything as a resistor. Basically anything that has a resistance is described as a resistor, right? Pretty straightforward in that sense there. So the fact that you have, light bulbs, and there's other stuff in here too. I mean, different kinds of light bulbs, different kinds of fuses, those apparently paper clips, coins, erasers, a dog. Okay. Don't electrocute your dog. Yeah. So you can see that but I'm just going to kind of be boring and just say everything is a resistor. Okay. Anything that has a resistance is a resistor. Okay. So that includes light bulbs or any other object, whatever. So I'm just going to be kind of boring and lame and just say everything is a resistor. But anyway, I want to switch back to the diagram. So this is sort of how, if you were to draw this out, again, on a piece of paper, this would be sort of what I would want you to see, okay? You have a battery, it's connected to a light bulb, and you can figure out stuff there. Now I'm going to turn back the values on. So you can see here, you can have a voltage of the battery and the resistance of the resistor. Now I think, there we go. So I can change this. Can I just type this in? Oh, it doesn't let me type it in. That's annoying. Yeah, I'll move it down to 5. Okay, there, 5 volts. And then this, I can change this resistance. What was it, 12 I think I had? Yeah, it was 12. Okay. So you'll notice when I did that, you have these red lines, these red arrows going through everything. So this simulates current, okay? And you'll notice basically it's sort of I believe it's the speed of the wire sort of translates to the strength of the current. So let me sort of raise this up a ton, for example. Yeah, so you can see I raised up the voltage a lot. That means since I've raised up the voltage, the resistance stays the same. That means the current going through this is going to be a lot larger, which means the arrow is moving faster. How high can I go with this? 120. Okay. But if I go back down, well, 0 is 0. But I'm going to go see, was that 5 before, I think? Yeah. So you can see it's sort of moving much slower in that sense there. And if I were to change the resistance, again, lower the resistance down. Whoa, okay. Yeah, 0 ohms, you can see basically this is a situation where if you have 0 resistance, it bursts into flames because you have just too much energy going through something. It's not going to work. Whereas if I move up one, yeah, okay, so there, it's not so bad. Still very fast, but then you can see as it slows down. And I'm going to get this to, what was it, 12? 12 before. Okay, now, a couple things you could do with this. How do I disconnect this, actually? Yeah, I have to just delete it. Yeah, let me delete that for a second. Let me lower this in. Let me put this back in. Okay, and I'm gonna change this back to 12. Okay. I'm purposely not going to connect it because what you could do is grab one of these. So this is, see, this is ammeters. This is a way of measuring current, and how this works is you basically stick it in the middle of the circuit. Okay, so you connect it there, and I'm going to connect it there. Okay, so now I have my current. It's going through the ammeter, it's measuring the current, and then which is basically going through all this wire. And so you can see 0.42 amps, and I believe what I had, 0.4167. So it's rounded, but you get the idea with that there. So that's your way of measuring current. There was another one. Is there a difference between these, really? Oh, okay. I think how this is supposed to work. So is you just kind of put this. Yeah. Okay. So this is not. I don't think there's an ammeter that actually just looks like this. I think you have to, like, in actuality, plug it into the circuit. But this is an easy way to just say, oh, what's the current here? 4.2. Okay. Or 0.42. Pretty straightforward in that sense. And again, if I were to go back to this and let me raise this up a ton, let's, screw it, go all the way up there. Well, this should be, what should my current be? Well, 120 is my voltage equals my current times my resistance. My resistance is 12. So 120 equals something times 12. Well, it should be 10. Yeah, 10 amps. So lines up pretty well with that. It's pretty straightforward in terms of how this all works. It really shouldn't be that complicated. At least in this sense here. Oh, is this to flip the battery around? Okay, that's not necessary. Oh, well, okay. There is something that you may notice. Which direction is the current coming out of the battery? It's coming out of the positive end, right? Remember, this long side was the positive end. So what this is saying is that you may think, well, wait a minute. If it's coming out of the positive end and going into the negative end, isn't that saying, like, it's positive charge? But, like, that's not what happens, right? It's electrons that move through the circuits, and those are negative charge. You're right, okay? What's happening is that, again, this goes back to what I said earlier, that this was all like stuff with current was all thought about before people even knew what electrons were. Okay, so when people were talking about positive and negative charges, they were just like, well, I don't know. Let's just say let's just say the current is positive, because how are they supposed to know, right? So they assumed current was a positive charge that moved through wires. Now they were wrong. It's the electrons, which are negative charges, that move through wires. So you'll notice here it says show current, and then there's electrons and conventional. So I could just switch this to electrons, and you see now they're moving the right way. They're moving from the negative charge of the negative side of the battery through the wire back to the positive side. This is what actually happens, okay? But it's the movement, so it's what actually happens is a negative charge moving around this way. And so you can see also, I could just switch this around. If I switch the battery, now the electrons move through the other direction, right? Same kind of idea. Now, the thing with that, though, is that they didn't think that. Again, they thought it was positive charge moving the other way. So this is actually how things are. It's a negative charge moving around, which would also therefore mean that there's a negative current, right? Because, again, current is charged over time. But, like, it's kind of annoying to just have a negative throughout all of your stuff. And so even when they realized that, like, they were wrong about it not being positive charge moving through everything, they just were like, does it really matter? Like, the numbers are the same, right? All that's different is the direction. That's the only thing that's different. The numbers are the same. And again, we don't have to worry about some stupid negative that's just always there. So they basically, even though they realized, a bit later, oh, we were wrong, screw it, this is good enough. Okay, so when we talk about current, in this class, just to make things simple, we're actually talking about conventional current. We're talking about the flow of positive charge. Just keep in mind that like doesn't happen, like, ever, okay? So any sort of time we're dealing with actual flow of charge, actual current, just have that thought in the back of your head that, like, in actuality, everything we deal with current here, it's actually a negative charge going the opposite direction. Okay, that's what's actually happening, and this is a description of positive charge going in this direction, which is not actually how it is, but that's what they thought it was, and yeah. So that's the basis of that, okay, to kind of get through that here. So this is, of course, a very simple example to start with. There's not exactly too much you can get with here. So you might think, okay, well then what's the point? How could I make this, more interesting? Well, you could, of course, add more resistors, right? And I could kind of connect these in an interesting manner. So, for example, I could do that. And I'm confused as to why nothing's happening. Oh, I know why. Because, okay, I know why. You won't know why, but there is a reason why there's no current going through that side at all. Unfortunately, again, I have to... Oh, okay, well, it works there. You could also add more batteries. For example, I could do... if this is gonna work. I think this will work. Yeah. So this is an interesting thing here, and you can see what is the now once I do something like this, now notice I have two different batteries, they have two different voltages, I have two different resistance with two different resistors. So my current here is 0.9, current here is 0.48, 0.42, 0.9, 0.42. You know, you're like, oh, okay, this is kind of weird, this is different. So this is where things get more complicated. When you start adding multiple things in, you get things that are much more complex in terms of how because again the current's different in different places. Oh, you could also use this here to measure voltage. Now this looks really scary, but really all you have to do is just put one thing there and just put the other thing next to it. But you have to put it on like the other side of thing. Hold on, it's not working. I have to put it. Oh, I think I have to put it in the circles. I think that's what I have to do with this. All right. Yeah. Okay. So you have to put it in the circles, basically. So this is saying that like between these two positions, you have 9 volts used up, right? So it's interesting how this kind of all comes into play and what works with all this. But you can actually get some interesting things here. So here actually 14 volts are used up. So you may notice some patterns by the numbers you show up here. For example, this has a voltage of 14. What's 5 plus 9, right? So you can maybe piece some things together, but you could also maybe imagine that like this can get really, really complicated. Again, this is just, I could keep going, right? I could add, what about if I have this here and this were to do that? And you know what? I'm gonna add another one. And then that one's gonna go. I'll just use a simple wire to connect this one to here, but I'm gonna use that to connect to that. I can't reach, damn it. Okay, so there. Now it's all crazy, right? What is my voltage and everything? Like if I put this here, then what? 9.5? Okay, right? You know what I mean? It's like super weird. Like, how does this all work? So there are rules for all this, and we will get into how this works on Tuesday. For now, you don't need to worry about this stuff, but this is coming shortly. Again, the base rules for this are not that complicated, but they get very complicated rather quickly. So, yeah. That's what we got for all this. Okay, let's go back to the things. I think I got a wrap-up question coming along. Yep, okay. The wrap-up question, just a fairly simple kind of math exercise here. A 1.5 volt battery is connected to a 5 ohm resistor. What is the current through the circuit? Okay, so give me time to calculate this, and so pause this, figure it out, and come back. Okay, so again, this is basically exactly the same as the question right above that. Voltage equals current times resistance. We have the voltage, it's 1.5. We need to know the current, and the resistance that we have is 5. So therefore, the current equals the voltage 1.5 divided by the resistance of 5, which is should be 1/3, right? Or 0.3. Okay, yeah, 0.3 amps. So yeah, again, it's pretty simple, right? This is very simple in terms of how you go about getting the numbers you want. But you can imagine once you get to things that are a lot more complicated than one battery connected to one thing, it gets a lot more difficult. But that's what we're getting tomorrow. So for now, you got some pretty straightforward stuff with the homework here. Okay, good. So here's your 2 homework questions. 12 volt battery connected to a 6 ohm resistor. Calculate the current going through the resistor. And then my laptop charger outputs 2.3 amps, 3.1 amps at 19.5 volts. How much resistance can the current cross with that voltage? Okay, so no real tricks with any of these questions, just kind of solving for various things. And you can see how this comes together. Again, today's stuff should be pretty easy, pretty straightforward. Tomorrow, we're going to get into some meat and potatoes. All right, so things are going to get a lot more interesting tomorrow. And it's one of those things that, like, I think most people hate, but I kind of love it. Because of just I don't know, it's interesting to me. So, anyway. Tomorrow you may hate me, maybe not. We'll find out.